This is SpaceTime, Series 26, Episode 40. Coming up on SpaceTime, discovery of one of the biggest black holes ever found, new clues on how the Earth's continents formed, and the redness of Neptunian asteroids shedding new light on the early solar system. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have discovered one of the biggest black holes ever found, a monster some 30 billion times the mass of the Sun. Black holes are the most intense gravitational wells in the universe. They're regions of infinite density in zero volume, places where the gravitational pull is so strong that nothing, not even light itself, can escape. Stars, planets, clouds of gas and other material are all attracted to black holes by the intense gravity. They then swirl around the black hole in an accretion disk, sort of like water swirling around the sink before it disappears down the drain. Material in the accretion disk is crushed, stretched and ripped apart at the subatomic level, releasing vast amounts of energy at billions of degrees, before eventually passing beyond a point of no return called the event horizon. Once inside the event horizon, escape velocity becomes greater than the speed of light, some 300,000 kilometers per second in a vacuum. And since nothing can travel faster than the speed of light, nothing, not even light itself, can escape a black hole. Here, matter is spaghettified as it falls forever towards the singularity, a place where the laws of physics as science understands them breaks down. But not all the material disappears down the black hole. Some of the superheated material on the accretion disk is deflected along powerful magnetic field lines away from the event horizon and then out towards the black hole's spin axis, where it can be accelerated to relativistic speeds and focused into intense superluminal jets called quasars. These quasars are the brightest objects in the known universe, shining out like beacons in the night, visible at distances of more than 13 billion light-years. Stellar mass black holes are formed by the death of some of the most massive stars in the universe in powerful supernova explosions, or through events such as neutron star mergers. While supermassive black holes, which are millions to billions of times larger, are found at the centers of most, if not all, galaxies. The so-called ultramassive black hole, which scientists have now detected, was found hundreds of millions of light-years away. It was detected thanks to a phenomenon called gravitational lensing, in which the mass of a foreground galaxy bends and magnifies the light of a more distant background object. Supercomputer simulations showed that the supermassive black hole at the center of the foreground galaxy would have needed to be some 30 billion solar masses in order to achieve the degree of magnification which the astronomers observed. And that places it on a scale rarely seen in astrophysics, hence the term hypermassive black hole. The findings, reported in the monthly notices of the Royal Astronomical Society, represent the first black hole found using this technique, whereby the team simulates the light travelling through the universe hundreds of thousands of times. Each simulation includes a slightly different mass black hole, thereby changing the light's journey to Earth. When the researchers included the ultramassive black hole in one of their simulations, the path taken by the light from the faraway galaxy to reach the Earth exactly matched the real images captured by the Hubble Space Telescope. The study's lead author, James Nightingale from Durham University, says it's one of the biggest black holes ever detected and on the upper limit of how large astronomers believe black holes can theoretically become. Nightingale says that most of the biggest black holes scientists know about are in an active state, where matter's pulled in close to the black hole, heats up and then releases energy in the form of light, X-rays and other radiation. However, gravitational lensing makes it possible to study inactive black holes, something not currently possible in distant galaxies. This approach could let astronomers detect many more black holes beyond our local galaxy and reveal how these exotic objects evolved further back in cosmic time. This is SpaceTime. Still to come, new clues about how the Earth's continents formed, and the redness of Neptunian asteroids could be shedding some light on how the early solar system evolved. All that and more still to come on SpaceTime. A new study claims the Earth's first continents weren't stable and were instead regularly recycled back into the planet's mantle. The findings, reported in the Journal of the Proceedings of the National Academy of Sciences, provides important new clues about planetary formation. The study's lead author, Associate Professor Fabio Capitanio from Monash University, says the rocks at the core of continents, which are called cratons, are more than 3 billion years old, and so formed very early in the Earth's 4.6 billion year history. He says they hold the secret of how the continents and the planet itself changed over time. To reach their conclusions, Capitanio and colleagues used high-performance computational modelling to simulate the evolution of the Earth's first billion years. They found that the first continents were unstable and recycled back into the Earth's mantle. Once the early continental blocks were back in the mantle, they melted and stirred with other material, eventually mixing thoroughly until they were, for all intents and purposes, gone. But the researchers found that some pieces of these original rocks can stay in the mantle for billions of years and eventually come back up to the surface. It's an important discovery because it shows that these first cratons are where important metals and other materials are found today. Capitanio also says the research shows how the planets formed and changed over time, including how the continents came to be and how they supported life, and how the atmosphere formed and changed as a result of the planet's tectonics. Over time, these recycled pieces of continent can build up under the new lithosphere, making it more buoyant and strong enough to stop more recycling. The study is unique because it explains how the continents are put together. Many observations of old continental cratons showed that they're far more complex and heterogeneous than the lithosphere of today. However, scientists didn't understand what caused the differences in how they formed. This study shows that parts of the cratonic lithospheric mantle still exist in the mantle today as disused, depleted heterogeneses at multiple scales that can last for billions of years. Relamination works best at high degrees of depletion and mantle temperatures that are similar to those of the early Earth. And that leads to the upwelling and underplating of large amounts of cratonic lithospheric mantle, which is referred to as massive regional relamination. It explains the complex source, age, and depletion heterogeneses found in ancient cratonic lithospheric mantle. Capitanio says this may have been a key phase of building the continents of the early Earth.
I found out that we really believe that the beginning of the Earth was a boiling cauldron with a lot of material that is extracted but then eventually gets recycled again in the interiors of the Earth and keeps on being transported in the interiors of the Earth. And eventually, with the process of separating scum from the boiling mantle, we form new crust, but also we have a trace of the old one that has disappeared. That was the observation we had, and our numerical model confirmed, give us a quantitative estimate of these processes, and also tell us how you can go from a boiling cauldron and slowly onto a stable continent. So basaltic crust to start with, then the granitic crust that separates in the way you're saying. So imagine a boiling cauldron and then something comes up and there will be the original basaltic crust. And as soon as you get the basaltic crust out, then eventually the part that is extracted leaves some part that is residual, and then eventually these blocks, they stay afloat together. And then eventually, with time, they keep on recycling again and again and come back again. And they grow slowly until finally the granitic, so the lightest, the very light part comes at the end. And this is the end of the process.
So it's a long filtering process.
It is. In our understanding, it can take 500 to 1 billion years, 500 million to 1 billion years in the making.
You put together some interesting computer modeling.
It's the way we understand processes that are so back in time and so deep, so large in scale that we wouldn't be able to address otherwise. This is unfortunately the limit of the science we do, natural sciences in general. We don't have the ability to prod the Earth and see how it reacts over time scales that are and spatial scales that are convenient for us. So we try to understand it with basic behavior described by some physical laws, and computer modeling helps us because it can reproduce those physical laws, not in a simple way, but in a very complex way. And the more and more these computer models become big and complex, the more these processes, they are clearer to us, and the more they are accurate in their description. So that's why we keep on going in that direction, modeling more and more details of how the Earth is made or was made. And something new comes out every time, surprisingly.
So you were simulating the early evolution of the Earth during its first billion years.
We found a number of processes, and in this latest work we published, we found essentially that this boiling cauldron keeps on separating the basaltic part, the scum that stays afloat because it's lighter in a way. But in this very long process of this, as I was saying, of the making of this early continents, as you were saying earlier on, at the beginning they keep on recycling and recycling, so they keep on going up and down until finally they stay afloat. In this making, we've discovered that the part that this original basaltic crust can be recycled easily, but we discovered that it stays in the mantle for a very, 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 very long time. So it can stay in the mantle for longer than a billion years. So what happens there? It happens that the making of the original continents, the oldest continents, in the end, they get the scum we were talking about, so the granitic crust that is evolved, but at the same time they embed all the other parts that have been recycled in the past. So what we do understand of the Earth is that we have some 3 billion years crust, which is the granitic crust you were talking about, which is the end one, or it's a crust that contains granite in a way. But we always found very tiny zircons, very tiny minerals that they tell us that the crust was formed at the beginning. So we're talking about 4.5 billion years, so the as old as 4.3, so really the beginning of the Earth. But they were recycled, so the only thing we find about those processes is just these tiny little pieces, like little minerals that are embedded in the later continents. That's what we simulated. We simulated that those processes, they keep on going like that. They're probably dominated by this recycling, and the traces, finally, we can map the motions of these little particles until they end up in the continents nowadays. So that was new in a way. We only had the geological evidence, but we didn't really understand whether that idea of the boiling cauldron is realistic or not, and in particular, how do you go from a boiling cauldron to a stable continent?
So you've got the coast of Hudson Bay in Canada, you've got some interesting areas in South Africa, Southern Africa, and of course you've got some beautiful cratons a beautiful craton which reaches the surface over much of Western Australia. Is this the sort of area you now go to confirm what the simulations are suggesting? Yeah,
well, I myself was in the Pilbara earlier on this year, and this is the point. So we do have two approaches. One, we go there and we observe directly what's going on in these oldest portions of the continents. There are some in every continent. There are some other blocks in South America, in Russia too. The Australians we have a lot of them in Australia, and are among the oldest ones. So the Pilbara is one of the oldest. That's why it's interesting. And the direct observation of these processes in the Pilbara tell us something about, as we were saying, the stable part. So the last part that forms. The original part is to be traced by terms of geochemistry. So we have to take these rocks, crush those rocks, but we've done this in the past. So in the field, this has been done in the past, and we have a wealth of observations that they really indicate that was happening. So this initial stage of the early continents, it's very active and very boiling and very bubbly.
This is important because this ongoing process, which has been happening for the last 4.6 billion years, it's dictated the evolution of life on Earth, the Earth's atmosphere, everything.
Yes. Well, that's the key, and we believe that the Earth is different from other planets because we have plate tectonics. Other planets do not have plate tectonics.
That was going to be my next question.
Okay, yeah. We do believe that plate tectonics is, in a way, a trigger or a cause for life, and therefore, by the same token, we think about other planets in the same term. there's no plate tectonics, no life. Plate tectonics, possibly these planets might have hosted or created the environment for life. Well, it turns out that the real atmosphere, the atmosphere as we see that today, started to be created on planets with those processes that were in the early Earth, so billion years ago, more than 2 billion years ago, that they are completely different from plate tectonics. So you have this recycling with the formation of crust, and then it's recycled again and formed again. And each time you essentially extract also relevant compounds that are relevant for life. So hydrogen, oxygen, nitrogen, potassium, phosphorus, all of those, and many others, of course. There's a long list. So now this becomes interesting. So if plate tectonics, which is unique to Earth, it's not really the origin of atmosphere and life, and other processes are, then of course we have to go back to the blackboard and think about how we think about life on other planets. Processes we observe on early Earth are similar in other planets, actually.
This is where things like boiling rocks at the ocean interface of places like maybe the Jovian moon Europa or the Saturnian moon Enceladus comes in.
Yeah, exactly. So this is really, in a way, a game changer. So it's not plate tectonics that creates life on other planets, but other processes. We observe those processes. My research now is moving on to Venus, because Venus is we have a little bit more understanding of Venus compared to Enceladus, other moons and other planets. Mars would be another target. So we can understand the evolution of those planets that do not have plate tectonics and try to understand and infer eventually what would have been the evolution of the planet and the atmosphere, and whether condition for life could have been possible or not.
Venus is a really interesting example. It's Earth's sister planet, but a twisted sister if it is. It's got an atmosphere which is 100 times denser than what we have here. Thick carbon dioxide atmosphere, 460 degrees surface temperatures, hot enough to melt lead. When you look at the geological features on Venus, they're very different from what we see on Earth. The overall scene on Venus seems to be one of maybe the crust was too thick, and so plate tectonics couldn't develop. Instead, the crust simply popped open to allow the planet to cool through volcanic activity.
Yeah. Well, this is what it is. So essentially the volcanic activity, as you say, the massive basalt flows. In a way, what we do understand is this is most likely what would have been the early Earth. So we were talking earlier on of a boiling cauldron and the separation of basaltic crust to start with. And on Venus, the crust can be very thick, and the basaltic crust today is thin, but in the early Earth was very thick. So we talk about 30 to 40 kilometers of basaltic crust, possibly. And that's why when we look at Venus now, it really looks like what could have been the Earth in the past. Besides, we always talk about basalt as an oceanic crust, but the truth is that if you don't have an oceanic environment, differentiated from a continental one in an initial early Earth, so likely those basaltic flows in the early Earth, they really look like those that are formed in a planet with a very thin atmosphere like Venus. But all this volcanic activity that you're talking about, all these massive basaltic flows that obviously regulate the way the planet cooled in the beginning, this is in a way what we understand being the early Earth. So Venus, present day, or the last billion years in Venus, very similar to early Earth.
That's Associate Professor Fabio Capitanio from Monash University. And this is SpaceTime. Still to come, how the redness of Neptunian asteroids could be shedding new light on the early solar system. And later in the science report, researchers have created a meatball made from the DNA of an extinct woolly mammoth. Gobble, gobble, munch, munch, yum. All that and more still to come on SpaceTime. A new study suggests that the asteroids which share their orbits with the planet Neptune aren't uniform, but rather exist in a broad spectrum of reddish colours, implying the existence of more than one population of asteroids in the region. The findings, reported in the monthly notices of the Royal Astronomical Society's letters, are based on observations of 18 asteroids sharing their orbit with Neptune, which are known as Neptunian Trojans. These asteroids are between 50 and 100 kilometres in size and are located at distances of around 4.5 million kilometres from the Sun. Asteroids orbiting this far away are faint and therefore very difficult for astronomers to study. Before this new work, only about a dozen or so Neptunian Trojans had been studied. They required the use of some of the largest telescopes on Earth. The new data was gathered over the course of 2 years using the WASP Wide Field camera on the Palomar Observatory in California, as well as cameras on the Gemini North and Gemini South telescopes in Hawaii and Chile, respectively, and on the giant 10-meter Keck telescope in Hawaii. Of the 18 observed Neptunian Trojans, several were found to be much redder than most of the other asteroids in the group. It's thought the redder asteroids form much further from the Sun. One population of these, known as cold classical trans-Neptunian objects, are found beyond the orbit of Pluto at around 6 billion kilometres from the Sun. The newly observed Neptunian Trojans are also very unlike the asteroids found in the orbit of Jupiter, the Jovian Trojans, which are typically more neutral in colour. The redness of the asteroids implies they contain a high proportion of more volatile ices, such as ammonia and methanol. These are extremely sensitive to heat and can rapidly transform into gas if the temperature rises, and so are more stable at large distances from the Sun. Now, the location of these asteroids at roughly the same orbital distance as Neptune also implies that they're stable on timescales comparable with the age of the solar system, around 4.6 billion years. And so they can effectively act like time capsules, recording the initial conditions of the solar system. Now, the mere presence of these redder asteroids among the Neptunian Trojans also suggests the existence of some sort of transition zone between the more neutral-coloured and the redder-coloured asteroids. It's thought these redder Neptunian asteroids probably formed beyond this transition boundary and were later captured into the orbit of Neptune. Astronomers hypothesized that the Neptunian Trojans would have been captured into the same orbit as the planet Neptune as the ice giant migrated from the inner solar system to where it is now some 4.5 billion years ago. That was caused by the migration of Jupiter and Saturn firstly in towards the Sun and then back out again, in the process moving both Uranus and Neptune further out and probably also swapping their orbital sequences from the Sun. The study's lead author, Bryce Boland from NASA's Goddard Space Flight Center in Greenbelt, Maryland, says the new work more than doubles the sample of Neptunian Trojans studied with large telescopes. Because astronomers now have a larger sample range of Neptunian Trojans with measured colours, Boland and colleagues can start to see major differences between the asteroid groups. The observations also showed that these Neptunian Trojans are even more different in colour compared to asteroids further out from the Sun. A possible explanation for this could be that the processing of the surface of asteroids by heat from the Sun could have different effects on asteroids at different distances from the Sun. This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with a science report. The fictional movie The Day After Tomorrow tells the story of the catastrophic climate effects following the collapse of the North Atlantic Ocean circulation. Now, new Australian research suggests that our own southern version of this deep ocean circulation pattern may be about to collapse. The study, reported in the journal Nature, shows that under future climatic scenarios, deep ocean warming around Antarctica is set to accelerate over the next 30 years. Scientists found that increasing meltwater coming from Antarctica will drive a slowdown in the circulation of nearby deep ocean water, which they say could weaken by as much as 40% by 2050. This circulation drives trillions of tons of cold, salty water down to great depths. As this water sinks, it drives the deepest flows of the overturning circulation, a network of strong currents spanning the world's oceans. The overturning circulation carries heat, carbon, oxygen, and nutrients around the planet, and it fundamentally influences climate, sea level, and the productivity of marine systems. The authors say the changes now being brought about by climate change are profoundly altering the ocean's overturning of heat, fresh water, oxygen, carbon, and nutrients, and those impacts will be felt throughout the global oceans for centuries to come. This report from the Australian Academy of Science.
My name's Matthew England. I'm a professor of ocean and climate dynamics at the University of New South Wales. I study how the oceans respond to climate variations and climate change.
My name is Adele Morrison. I study oceanography at the Australian National University in Canberra.
At the centre of their work is how water moves around the planet. Surface currents are powered by wind patterns, but deep underwater currents are driven by different layers of density in a process known as overturning circulation.
The ocean plays a big role in global climate by moving heat and carbon and also nutrients around, which affects ecosystems in the ocean. Changes that happen in one small location, like say near Antarctica, can then have a global influence because those waters move all throughout the whole planet.
And it's the Antarctic overturning circulation that has these scientists worried. They're two of the authors of a landmark study published in Nature that makes a dire projection closely related to the melting of the ice caps.
And what we see in that simulation is that the meltwater rate that we expect to play out over the next few decades is enough to slow down that overturning at a very dramatic rate, about 40% reduction by 2050.
Meltwater is a clear consequence of climate change. As ice caps melt, huge amounts of fresh water enter the oceans. The resulting reduction in salinity makes the water much less dense, meaning it doesn't sink with the same force.
So the dense water is important because it's a major driving factor in the global overturning circulation, which is this conveyor belt of waters that move around the whole ocean. And so this formation of dense water pushes that water down into the abyss, and then throughout the rest of the global ocean, that moves up again in different places around the globe.
A slowdown in the overturning, particularly by 40%, would have a profound impact on marine ecosystems.
The thing about the oceans is that all of the marine life that we have at the surface, when it dies off, it sinks to the bottom of the ocean. So there's a lot of nutrient-rich water in the ocean abyss. If we slow down the overturning circulation that brings that very bottom water back up to the surface, we cut off a way that nutrients get back to the surface to regenerate marine life.
Their projection is based on advanced modelling that doesn't just factor in meltwater, but captures key regions of Antarctica with unprecedented skill.
And this is particularly important around Antarctica because there's a lot of small-scale processes that are important for this dense water formation.
A slowdown of the North Atlantic overturning circulation has already been documented. But this latest study shows that overturning in the Antarctic region could decelerate at twice the rate.
I should also say there's actually evidence in the ocean abyss that the mechanism we've described is already playing out. There's been significant warming of the ocean abyss, and that's exactly what our model projections show, that as the ice melt slows the overturning circulation down, you do get a warming of the ocean abyss. And if anything, our models are a bit behind where the observations are already tracking. So all the evidence we have suggests that we will have a slowdown of this overturning circulation in the next couple of decades.
And that report was provided by the Australian Academy of Science. A new study shows that people on vegan diets tend to be healthier. The findings, reported in the Journal of the American Medical Association, looked at health records for more than 125,000 people across the United Kingdom. The authors found that a healthy vegan diet was linked to a lower risk of heart disease, as well as a lower risk of cancer and other forms of premature death compared to non-vegan diets. However, the study also found that vegans who drank more sugary drinks or fruit juices, and those who ate more snacks, desserts, refined grains and potatoes, still had a higher risk of these conditions and premature death compared to non-vegans. Scientists in Australia have created a meatball made out of the DNA of an extinct woolly mammoth. It's part of a project by a company called Vow to demonstrate the potential of meat grown from animal cells without the need to actually harm or kill animals. Scientists at the University of Queensland began the project by creating mammoth muscle tissue protein using the DNA sequence from woolly mammoth myoglobin, a key muscle protein which gives meat its flavour. And they filled any remaining gaps using elephant DNA. The sequence was then placed in sheep myoblast stem cells, which then quickly replicated and grew to some 20 billion cells, which were then subsequently used by the company to grow their mammoth meatball. Right now, there are many companies working on cruelty-free lab-grown so-called cultured meat products. But most of these are focusing on things like beef, chicken and pork. But this company is going for more exotic tastes, like alpaca, buffalo, crocodile, kangaroo, peacocks and various types of fish, with Japanese quail to be the first cultivated meat offered for sale. Apparently there's already a big market for it in Singapore. The company chose the woolly mammoth for this trial because it's a symbol of diversity loss and a symbol of climate change, having been driven to extinction by a combination of hunting by humans and a warming world at the end of the last ice age. They initially wanted to produce meat from the now extinct dodo bird, but sadly the DNA sequences needed for this work simply don't exist anymore. Now the only test left for their 400-gram mammoth meatball is the taste test. A new study in the journal Scientific Reports has confirmed the safety of genetically modified crops. Scientists analysed over 6,000 published papers on GMO corn over the past 20 years, looking at research focusing on differences in productivity, toxicological and environmental differences between GMO and non-GMO corn. The analysis, which is based on data from studies conducted worldwide, showed that genetically modified corn crops had yields 5.6 to 24.5% higher than non-GMO corn varieties. Now, this contradicts one of the chief anti-GMO Frankenstein food arguments that genetically modified corn had not increased crop yields. The study also showed that genetically modified corn crops had statistically significantly lower levels of mycotoxins, a toxic metabolite from fungi that infects corn crops. In fact, they showed up to a 36.5% reduction in these mycotoxins in GMO corn. Tim Mendham from Australian Skeptics says the findings show that not only are GMO corn crops fundamentally safe, but they may also be safer than conventional corn.
This was a meta-study looking at 6,000 already published papers on GMO corn, and it's suggesting that GMO products are not only safer for you, they have a higher yield, and that they are better all around. Now, what they're saying is that, especially compared to organic products, organic in quotes is in many cases a bit misapplied, but there's a lot of pseudoscience about organics, and there's a lot of pseudoscience about genetically modified GM crops. Certainly, they are in the green movement. The GM crops are the bête noire. They're horrible. They're anti-nature. They're evil, and they'll come to get you at night. The issue is when you actually crunch the numbers, and that's what this particular meta-study did, using data from around the world, from 6,000 papers. They found that genetically modified corn crops had yields between about 6 and 25% higher than non-GMO corn varieties, which actually contradicts a lot of the arguments that were made by people who are against it. The study also showed that these GMO corn crops have statistically significant lower levels of mycotoxins, which is a metabolite from fungi that infects corn crops. That's part of what they build into these GM things, sort of resistance to a lot of nasties and pathogens and things like that. In fact, these GM crops showed a reduction of about 37% of mycotoxins compared to standard crops. You take it one step further and you compare it with organic crops as well as just ordinary things, and the differences become quite dramatic. And even though the people keep saying that GMO crops are dangerous just because they're man-made, in quotes, the reality is that it's not necessarily the case. And so the blanket assumption that GM bad, organic good is not necessarily borne out by the numbers. This was looking at 6,000 studies.
What makes something organic? What are the principles associated with that?
The principles of organics is a broad range of things. There are areas that are certified by various organic growers groups. You have to wonder sometimes, quite frankly, and people have wondered about the bona fides of those groups. Then again, you get that sort of thing in all sorts of products. So, an organisation is made up to give endorsement to a particular product. You find that everywhere. So it's not just organics. Organics are supposedly natural products that don't have any artificial additives put into them, and that includes pesticides and fertilizers, artificial fertilizers. And they grow these products. The growers get very sensitive about any crops nearby that might not be organic and that might be polluting their crops.
Put ram's horns in the corner of the field or something like that?
That's the extreme end of it, right? That's the biodynamics of organics, and they are adding things to it. They're adding the sheep's horns and burying things at midnight and all sorts of stuff. It's associated with, I think, a Steiner philosophy of how you should grow food, and it drags in a lot of...
Steiner or Stoner?
I think is it?
That's all right.
Was that one of your jokes?
Yes.
Oh, sorry. Anyway, you have to follow all these things about how to sort of grow your products. And biodynamics is a little bit popular in some wine growing, but you sort of take people aside and do proper taste testing of these products. You're not going to get a lot of difference. A lot of it's in the mind. But yeah, that's the extreme end of organic. Basically, it is this concept of natural, and the concept of natural is a very fluid thing that just because something is natural doesn't mean it's good for you, or it doesn't mean it's more efficient. And a lot of things that I claim using the justification natural is not enough. A lot of poisons are natural.
Well, yes, pyrethrum.
Yeah, so yeah, all sorts of things. There's hemlock that are natural that aren't what?
Crocodiles are natural.
Yeah, a lot of things that are sort of natural is not necessarily good for you just by itself. So using that term, it's natural, is dodgy. Not to mention the fact that a lot of things sold at the supermarket as organic or natural aren't. You've got to look beyond the hype, beyond the marketing, beyond the good intentions of people. Is it accurate? And you could say, is every GMO, is every genetic modification good? Probably not. Is every organic good? Probably not. So, life's a bit tougher than simple explanations.
That's Tim Mendham from Australian Skeptics. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favorite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more space time, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel. And on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.